Welcome to today's library seminar titled Democratizing the Creation of Custom Models with GOES and NEXRAD Data. I am Lisa Clark, Reference Librarian at the NOAA Central Library. This presentation is part of the NOAA Innovators seminar series, which is put out by the NOAA Technology Partnerships Office. Tiffany House, Commercialization Specialist for Small Business Innovation Research, will introduce our three speakers. But before we begin, here are a few logistical tips to help you enjoy our presentation. If you're having trouble with the audio or visual components of GoToWebinar, please log out and rejoin us. This resolves most technical issues. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel, as well as the Library Seminars website later today. We will also be accepting questions throughout the webinar, which the gentleman will address at the end of their presentation. Please feel free to type your questions in the question box on the right side of your screen at any time. So with that, I thank you for attending this library seminar and turn the presentation over to Tiffany.
Thanks, Lisa. Welcome, everyone. My name is Tiffany House, and I have the pleasure of introducing the speakers and briefly describing the Small Business Innovation Research, or SBIR program. The mission of the SBIR program is to support scientific excellence and innovation through the investment of federal research funds in critical American priorities and to build a national economy, one small business at a time. This is done through a competitive awards-based program which enables small businesses to create innovative products and services with commercial potential. Onai is one of our unique presenters at the NOAA Innovators series, as they recently completed their phase 1 effort with NOAA SBIR funding. Typically, the NOAA presenters are companies that completed their phase 2 effort. The difference is that phase 1 is the proof of concept phase, where awardees are establishing technical merit and feasibility of the proposed effort. Phase 2 is the research and development phase. So Onai is ahead of the curve, and I would like to add that their technology is available for phase 3 and can be acquired through a sole source procurement. And if you have any questions about that, feel free to reach out to me after this presentation. NOAA's Big Data project has made available several valuable weather satellite and radar station data sets. While a critical first step, many organizations that would benefit from the data are not technologically capable of easily performing state-of-the-art machine learning. Unlocking the power of the data for those who can most benefit, Onai will demonstrate a browser-accessible tool that enables users to automatically build deep learning models and leverage NOAA data to address their own challenges. Headquartered in Silicon Valley, Onai's world-class team is developing the future of decentralized computing and machine learning technologies with a focus on addressing real-world challenges. The speakers bring expertise and groundbreaking computational capabilities together with a desire to maximize the positive real-world impact of NOAA's dataset. I'm very pleased to welcome Guha, Shafani, and Galana.
Thanks for that introduction, Tiffany. We're really happy to be here. Good afternoon to everyone in the DC area. Here it's sunny out there today. It's a nice sunny morning here in California also. My name is Guha, and on behalf of the team at Onai, I'm happy to share with you about work that we performed earlier this year to make accessible the power of artificial intelligence on rich weather data. I'll start off with some quick background and then turn it over to Galana to discuss why this is useful. And then Shrifani will show a demonstration. We'll close with next steps and a bit more about our company. And we're going to leave plenty of time for questions. So please do submit any questions or ideas that come to mind to Lisa, and we'd be happy to chat about it at the end. As many of you know, the GOES series of geostationary weather satellites scans the continental US every 5 minutes and provides incredible meteorological imaging data. GOES 16 was the first in the series. 2 more satellites are scheduled for the next few years. NEXRAD is a ground-based weather radar system. It provides very rich data, including on precipitation. NOAA makes available to the public dumps of the data from both GOES and NEXRAD. So this is an incredible resource that NOAA is contributing to the world at large. For the past few years, it's made these large data sets available through popular cloud computing providers such as Amazon and Google. So I'm going to switch to something that might seem a little unrelated, but let me just quickly introduce the concept of machine learning. Machine learning is a form of artificial intelligence. Machine learning algorithms build a model based on training data in order to perform inference. What does that mean? It means that we show the algorithm many examples from which it learns, so that when we show it data that it's never seen before, it's able to make predictions. There's a particular form of machine learning, a particular algorithm called deep learning, which has really revolutionized the field in the past several years. What you're seeing here is a cartoon representation of something called a neural network. A neural network tries to figure out how to combine and recombine different features of the data to be able to generate predictions about some other feature. So data is going into each of those nodes you see at the bottom, and the outputs at each level are getting combined in different ways, weighted in different ways until you get your answer at the end. Neural networks were originally inspired by the human brain many decades ago. They proved to be overhyped, actually, until a renaissance in the past 5 years, when it was realized that by making the networks have many more levels or be deeper, that's where the name deep learning comes from, you could do amazing things. And a lot of you have probably heard about many of these accomplishments. If you've heard of AlphaGo, a program from Google that defeated a grandmaster at the game of Go, that was using deep learning. Deep learning has also learned to play and win video games. It's used for robotics. It's used for translating languages with astonishing accuracy. And it's even being used more and more in medicine, for example, to analyze CT scans. So in many ways, deep learning is a magical technique, but it's very challenging. It requires expertise in the methodology, and it can require fairly high-end compute hardware. It's quite compute intensive. So that's the world as we found it. On the one hand, amazing data resources from NOAA, and on the other hand, amazing computational techniques in which we have a great deal of expertise. I'll turn it over to Galana now to talk about why we felt the logical next step in the story of these data sets was to introduce them to deep learning. Galana?
Thank you, Guha. Hello, everyone. My name is Galana. It's nice to talk to you all. As Guha mentioned, deep learning is very difficult. So with that said, and really out of the way, would like to address the question of why is it worth using deep learning for weather data, and who all can benefit from this? As probably all of us on the webinar know, weather is critical to many different fields. It's absolutely crucial. People can more rigorously incorporate weather into predictions they make that are specific to their domain. That can make a huge difference to them. And there are several use cases that may benefit from our innovation across a wide range of fields. To name a few domains, agriculture, building sustainability, fire safety, construction, shipping, air quality control, and ocean ecology. For example, in agriculture, weather is obviously one of the most important factors. We can allow growers to supply their historical yield data and automatically build them a model that shows how weather influenced this yield. They can use this to make decisions going forward, or even make predictions about the present growing season. Or another example is wildfires, which has been a huge issue in California and really across the West Coast this year. Can we allow firefighting agencies to geographically make fine-grained predictions based on present NEXRAD readings? Similarly, for shipping, air quality efforts, the list of examples really goes on. Basically anything that involves weather. NEXRAD data is so rich and weather is so critical that we could offer huge benefits by allowing people to apply the power of deep learning, NEXRAD data, plus their own data. Once you understand the why, the next question is how to make that possible. We already said that deep learning is difficult. So what can we do to democratize this power and allow those who can benefit to actually see those benefits? And this diagram here shows our model. To explain, what we have done is built a system that allows someone to supply their own domain-specific data, for example, crop yield data, which we'll get into more shortly. And then we integrate that with NEXRAD data to build a model for them that they can use to make predictions, gain insights into their specific domain. For example, going back to agriculture, a grower can easily provide their yield data and location information for some time period, build a model, and then obtain predictions based on that model. We'll go ahead now and turn it over to Shrifani, who will do a demonstration for you.
Okay, so this is our interface for the prediction task that Galana discussed. The typical pipeline for any machine learning problem, the typical components involved in training in solving any machine learning problem are, first of all, ingesting the data, subsequently training a model, and then finally predicting on unseen data, and that's the prediction task. So through our user interface, you can obviously specify what training data you want to use to train your machine learning model. So in this case, our interface allows you to specify, for instance, URLs from where you can pull in the train and the test the data that you want to predict on. Specify additional parameters like which column in your data set you want to predict on. And if there is geospatial or temporal information, then you can specify that as well, because those need to be handled a little differently. So in this particular example, we're using the pure database, which contains information about pesticide use. And we're trying to predict how much pesticide is being used. And then there's obviously some geospatial information to go with it, and there is some temporal information to go with it. In addition, there's a variety of ways you can incorporate this information. So training a new model, as you can see in the menu option above, allows you to train a new model. Now, the big realization with deep learning is that it's not merely the parameters or the columns in your data set, but it's how you combine them. And you combine them in very complex ways, which is where the term depth comes from. That allows you to really unlock high performance on your data sets. Now, what particular combination gives you the best performance is actually a very involved challenge, and people end up spending months to years finding the best combination. The technical parlance for this is architecture. It's how your features are being combined, how your data set attributes, your table columns are being combined, and how complex is that combination. The deep learning terminology for that is architecture. So you can obviously supply your own, but we allow a special feature where you discover a so-called good architecture for your problem. And this is using some latest AI research that allows us to, cut the time taken to find the right feature combinations for your problem from, say, several months to basically a few minutes. And in this particular case, I want to make a prediction about how of pesticide use. And in our case, you fill out this form and you hit submit. and it starts chugging away and gives you a ticket number that you can, when this thing is done, you can see a geospatial visualization and you can see some histograms showing importance. So I have an existing run right here from a previous run. And so you can see on the right, we have a histogram showing the importance of the NEXRAD, of the various attributes in the NEXRAD data, which I'll go over in a second. And in the back, you can see a geospatial visualization. And this is predictions at the locations of various NEXRAD stations. And ideally, those dots that you see here, the radius corresponds to the prediction values at those locations. In this case, all the attributes are, all the predictions are very close to each other, so there's not a lot of variation in the points, but assuming you had byte variation, you would see different size dots. On the right, you have what we call feature importance in this histogram. Now, feature importance is, it's for the columns in your NEXRAD data, which includes various columns like precipitation, precipitation over time, reflectivity, which is some other metric, and so on. And your importance is a value between 0 and 1. And higher importance specifically means that that column is more vital, more informative to the model when it's making a prediction. So in this particular case, the base reflectivity is the highest, most informative column in NEXRAD data for your particular problem case. And subsequently, there's a geospatial visualization at the bottom that is, you can pan, zoom, and explore, whatever results you have, and you can see how this varies with, across how the geography contributes to the variation, essentially. And that is, what we have. So, yeah, that's what we have. So if we can take it back to Guha.
Thanks, Shrifani. So just to summarize the demonstration that Shrifani just showed, what he walked through there is an example of how somebody can provide their own data that's specific to their own use case. So in his example, it was a data set related to pesticide usage, the pure data set for California. The system already knows all the NEXRAD data. And so it automatically is bringing together those two data sets to try to learn a good predictive model for the quantity that the user is interested in. And it's what Shrifani showed you there, gave you a little bit of a peek under the hood, introducing concepts like architecture. But really the goal here is that a non-expert can use this system. So if you don't know anything about deep learning, but you do know your own field, whether that's agriculture, whether that's fighting fires, whatever it might be, that should be enough. You should just need to submit your own data, specify what it is that you care to predict, and the system should be able to handle everything else to figure out how is weather data predictive of what you're interested in, if at all. So another possible outcome here is, of course, that the system determines that really weather is not related to what you care about. So if you're submitting a data set related to winning lottery numbers, NEXRAD data is unfortunately not predictive of lottery numbers. So the system is going to basically show you that in that histogram, it's going to show you that nothing is really predictive. But if there is something that's predictive from NEXRAD data, you'll see a nice visualization on the map showing you the predictions at the different locations that are specified in your data set. So for example, in this particular one, it corresponds to different growing locations. So the goal here is something that non-experts can use, but it's hiding a lot of hard technical questions that we had to answer so that other people didn't need to worry about it. So just to quickly run through some examples of those questions, one issue is at what resolution do you need to consider satellite imagery? So for example, let's say that you're trying to use cloud cover and you want to figure out cloud cover data from the GOES images. At what resolution do you need to use that image data? Another example is the size of the data sets that are involved here. These are very large data sets. How best can we store them? How best can we structure them so that when a query comes in, we're able to efficiently look up those portions of the NEXRAD data that are relevant to the given problem. Another example is how to measure the impact of various data. So Shrifani mentioned that histogram. How do you actually go about judging the relative importance of different features from NEXRAD data or from the user's data set to their given problem, even if it's just for informative purposes. Other examples of questions are how do you get the data to be up to date? How do you structure a workflow so that it's natural to an end user? These are the types of things that we had to think about, not to mention some of the other kind of hard questions around architecture and issues like that. Lastly, let me take a step back into the context of what we do as a company. We bring together large-scale decentralized computation with machine learning, with cryptography, and that's an excellent combination for taking forward the type of system that Shrifani showed you. Our next steps focus on using those strengths to really see this platform used more widely for real-world practical problems. For very large learning problems, sizable amounts of compute are useful, and we have methods for providing those compute resources. Secondly, we've made this platform to allow general deep learning to be performed on NEXRAD data. But the reality is that every industry that Galana mentioned is different in some way. Today, our system is useful, but it's a general solution. Fortunately, with our platform, everything is open, so others can come and build on top. For example, someone could come and build a dedicated tool on top specifically for solar installers, or for firefighting, or for whatever use case they would like to target. And the last thing we'd also like to introduce beyond what we discussed here is how to provide guarantees to users that their sensitive proprietary data is secure and there's no danger around data leakage. So there are a lot of exciting things to be done here. We're proud of what the team has already accomplished. We think this is already a very useful technology, but we're also excited about what's to come and really getting this out there in a way that we can see it have major positive impacts. So please do contact us if you have any ideas you'd like to chat with us about. On this particular project, we look forward to collaborating to make this platform more available to NOAA's stakeholders, including the public. We're happy to make this technology available to you in additional forms. Please do get in touch if you have creative ideas. Beyond this project too, we'd be happy to hear from you if you're working on projects that entail the use of large amounts of computation or involve citizen science. We'd love to help. So with that, thanks for attending. Hope you enjoyed your lunch. And Lisa, we'd be happy to answer any questions that might have come in.
Excellent. Thank you so much. We do have some questions, but before we start, I read them to you. I want to remind the audience that we have up 30 minutes to answer your questions. So please continue to type them in the questions box. You'll see that on the right side, it's a chat box, and I will continue to read them to our speakers. The first question asked, if fault is found with deep learning, how do you troubleshoot to origin?
Sorry, what was the last word there?
To origin, O-R-I-G-I-N.
That's a really great question, and that's actually a very insightful question for the field of deep learning as a whole. How do you? There's kind of two parts of that question. One part of that question is how do you even know that something has gone wrong? And then the second part of that question is if you know that something has gone wrong, how do you figure out where it's gone wrong? So for the first part of the question, really the best we can say is that we can apply standard techniques here. So the first of those is using your own understanding of what is a reasonable result, just to make sure that this passes the bar of reasonability. The second thing is a more technical answer, which is to use cross-validation and other standard statistical techniques to make sure that the learning has converged and that there's not overfitting going on. And these are things that are already part of the system. So the system is already automatically ensuring that it's doing the learning in a robust way. Now, the second part of the question is a harder one. So the second part of the question is, let's say that you look at the results and they don't look reasonable to you. How do you figure out where something has gone wrong? That's a much trickier question. So what we can say is that if something has gone wrong, given the statistical checks that are being done, it's not because of something that's gone awry in the learning process. It really is something in the data that's been fed in, or that there is important data that's being left out. And so that's something where really there's not too much that we can do in an automated fashion to help you figure out what's missing. It's like, how do you know? It's from the computer's point of view. It's kind of like, how does it know what it doesn't know? And so that is actually a challenge across the field of deep learning in general.
Great. Thank you for that answer. Another question asks, how much data does the user need to provide?
Yeah, so that's also a excellent question. So Shrifani, I'll turn it over to you in a second if you want to give some examples from other common learning problems. But what we found on this use case was that you don't need that much data. Fundamentally, it depends on how much variation is there in what you're trying to predict. How complicated does the model need to be? The simpler the predictions, the simpler the model, the less data that you can get away with. Even with, for example, several hundred rows. So the common data sets that we saw used here when we mainly have shown this to people in the agriculture field. And so there, the common data sets correspond to yields in different locations. Or for example, you might have data going back several years. So you're varying across both location and time. So neither of those are going to be data sets that are all that large. Especially they're not going to be that large compared to the NEXRAD data itself. But Shrifani, maybe you want to kind of zoom out there and give some more general context for the typical data sets that are used in deep learning.
Sure. So yeah, like for say machine learning that was predating deep learning, there is theory for what sort of data sizes you need for say, and that depends usually on the number of columns in your data and let's say how tough your prediction problem is. So it turns out for deep learning, a good rule of thumb is as much as you can bring. But you don't always necessarily need millions or billions of data points or tens of thousands of data points. So it's unique to your problem how much you need, and usually there's a bit of trial and error to figure this out. So if you look at, say, domains like natural language processing, where you're trying to make inference or prediction about natural language text, or if you're looking at vision, where you're trying to predict attributes about what kind of object is in an image and so on. You're usually in the regimen of several 100,000 to several million data points, but those problems are unstructured problems. So the model likely is having to do a lot more work there to say unravel language or unravel images. Now, the problems that we're dealing with for this use case are more structured. So the need for data sort of decreases for that use case. So
Yeah,
it's a trial and error thing.
yeah. So I think in the example that Trifani showed you, there were several hundred data points in what the user provided data set contained. And the other thing here is that the system can give you some help here. So given that it is doing checks on convergence, if your data is too small and the model is not even able to converge, it's going to tell you that.
Excellent. Another question asks, how well does the NEXRAD model predict NEXRAD data? Is the model static?
That is a really, I think, smart question. We should go and check that. So we have not tried that. I'm not sure what the answer is. I think that would be interesting to see, both from the point of view of how predictive are given NEXRAD features of other NEXRAD features, and it would also be interesting to look at it over time. How predictive is a given year to another year? One thing I can mention is that we did do some feature expansion on the NEXRAD data. So for certain fields that were extremely fine-grained, we ended up computing percentile quantities for those particular columns. So that would also be interesting as a check to see how predictive are those columns of some of the other features. So yeah, that's definitely something that would be interesting to look at.
I don't remember Google put out some work recently where you try to predict the same Doppler radar data a few hours in the future, and it seems to work very well. Now, with NEXRAD specifically, I don't know, but it seems like both of these are in the same domain.
All right, next question asks, have you thought about correlating NEXRAD with GOES data in any way?
So with the GOES data, the way that we've primarily thought about it is that it is a data set from which we can derive columns to add to the NEXRAD data. So for example, we trained a model that quantifies cloud cover from the GOES image data, and then basically adds those as extra columns onto the features that NEXRAD is already providing. So we've mainly thought of GOES as kind of an augment. And if somebody has a use case where there's some particular aspect of the image data that they feel would be useful, we can basically train a model to try to extract that out of the image, turn it into something numerical that can be then used in the overall pipeline.
Okay. Next question asks, how would you verify that user-loaded data is appropriate for your model to prevent misrepresentation?
So from the point of view of the system itself, it has no insight into the broader context of what data means. It's just a bunch of numbers. I mean, this is why AI is not going to replace scientists anytime. So they don't. The system itself, the best that it's able to do is to tell you whether things have converged, whether the results on a validation set that's been held out are good or not. So it can do those types of things to help you have confidence in what it's providing, but it can't replace the human being in the loop to basically be a judge of, is this something that's even reasonable to ask, and do the results make sense?
Excellent. I have one last question here. The question asks, how do you handle updates? If there is reconfiguration of GOES or NEXRAD, are those configurations automatically and verified in your model?
Yeah, so that's a really great question. That's been a very active area of work for us as we've continued on this beyond our actual SBIR project. So there's multiple challenges here. One is, how do you efficiently update the data structures? Because when we're accessing this data to be able to use it in model training, what we're really accessing is data structures that we've constructed out of the raw data. If we were going back to the raw data every time a query came in, it would take days to answer. So what we're doing in reality is that we have a pipeline that takes the raw NEXRAD data, does processing on it, constructs certain data structures, and then keeps those data structures available when queries come in. So what we're doing is basically, when there's new data sets, we're updating those data structures. There's a related challenge here, which is just the actual sizes of the data and certain standard sort of messiness in the data. So like any large data set, the data is not perfectly clean. So when you're doing that sort of loading up of the data and the data structures, you have to be doing the appropriate checks to make sure that, for example, missing columns are dealt with and things like this. So one of the areas that we've been doing a lot of work recently, even outside of this project, is how do you do high performance, accessible, large scale data storage for these types of very large data sets. So that's kind of the two halves of the problem as we think about it. One half is, how do you store it in the first place in a way that can be accessed very quickly? And the second half is, how are you constantly updating these intermediate data structures in a efficient manner?
Great. We just got one other comment. Someone comments, brilliant logo for Onai, by the way, and thank you for your answers.
Oh, thanks. I'll pass it along to the team. Yeah, we really enjoyed working on this project, and we hope to remain engaged with NOAA going forward. Thanks for everybody who attended.
Oh, excellent. Yeah, I believe that's our last question then. Any last comments from any of the other speakers?
Galana or Shrifani?
No, it's not for me here.
Okay, right. Well, thank you very much. I just want to remind the audience that since this webinar was recorded, we encourage you to share the link with interested colleagues or watch the beginning of the presentation if you joined us late. You can find the recording on the NOAA Central Library YouTube channel or the Library Seminars webpage. And I'd also like to thank our speakers for giving sharing their experience and time with us, especially on early California time, and to Tiffany for organizing today's NOAA Innovators seminar. And to the audience, I truly appreciate that you joined us. NOAA Central Library is very proud to present the work of the NOAA community and its partners, and we hope that you will join us again. Be well. Take care.
Thanks, Lisa and Tiffany.
Thank you, guys.
Bye.